And with that, let us conclude some of the lessons that we can learn from what I just discussed. First, that even addition can be complicated with multi-threading. Second, there are inefficiencies because if you think about it, spin waiting, looking and waiting forever is not the most efficient piece of code you can write. Uh, especially if there are many locks that many threads are cannot progress because of other threads holding locks. This can significantly slow your parallel program. Actually, there was a paper a couple of years ago, scientific paper, a few years ago from people at basically Microsoft Research, now at Google Research, who basically looked at some of the implementations for data analytics that use parallel programming slash distributed programming and some others that use just um, a single computer basically. And the single computer results were much better than using parallel programs. Modern compilers and architectures do reorder the instructions. We have actually focused on that quite a bit until now, making simple reasoning more difficult because this might be, I mean, you might look at the code and think this code is fine. I mean, what is wrong with me adding one here and two over here? But what happens is that the instruction ordering can screw up things pretty fast. And the more you have threads and the more you have processors. So if you, for example, right now there are machines with 128 cores. If you're talking about GPU programming, then you're basically talking about hundreds to thousands of cores, right? So how do you parallelize in that way, given that each one, given the number of threads that you have? One thing that you can read that would be a fun read is Peterson's algorithm. You might want to just take a look at it. So now we are back to three easy pieces. From our introduction to concurrency, we know that one of the most fundamental problems in concurrent programming is basically identifying the critical section. Where are the parts which you actually want to run atomically? Basically, either all of them would run together or none of them will run. So you would want to basically be able to identify these parts in your code. And parts of these operations that you would want to be atomic are those operations that access shared objects, shared data. So if you have a variable x that is being accessed by multiple threads, you must take, I mean, this will be definitely part of your critical section. This can also be the shared program state, some variables allocated in the heap, e.g. using malloc, for example. If you're using malloc in C, there are ways to actually handle shared objects. We'll talk about some of them. One of them is basically having barriers. Memory barriers are basically instructions that prevent compilers or the hardware from reordering memory in some sections. So you can use a memory barrier. That's a concept that you can actually look up online in programming. And that would basically mean that no access before the barrier can move after the barrier and vice versa. So you basically tell the compiler, you know what, optimize everything before that, but you cannot optimize after this, but you cannot optimize such that anything before my barrier comes after my barrier. And the bounded buffers that we are actually going to talk about today. Locks, as we said, are used to synchronize. They basically are used for mutual exclusion. When one thread holds a lock, no other thread can hold the same lock. You use lock acquire, and basically, if you acquire the lock, all other threads will wait until the lock is free. Then we'll be able to take it. Then there is the lock release, where you actually release the lock. And if all lock holders finish and no higher priority waiter eventually gets lock. This is basically liveness. I mean, if you have prioritization, so if you have a lock, someone holding that lock finishes, then you got to pick one of the next processes or threads in line to actually acquire that lock, and then you basically look if there are any processes that do have, for example, high priority. Then you would pick these. If none are available, then you'll pick the next priority ones. So eventually, all threads will acquire the lock. So we can use locks to actually handle critical sections, as we will see in the next few slides. Okay, so you add a lock around the lock acquire before the critical section, and the lock release after the critical section. So one example of such critical sections is, for example, any place where you have additions on a shared variable, like balance equals balance plus 1. And this can be also, for example, if you're adding an element to a linked list, removing an element from a linked list. I mean, of course, addition and subtraction are the same. Okay, so any updates that you do to a shared structure, map, a dictionary, whatever, you need to actually lock it. Okay, also files. So I mean, if you're writing to a file, it's almost exactly the same procedure. To use a lock, this is actually C code. We add basically a lock acquired and an unlocking. And here you have basically lock T is lock thread, mutex. So you start a mutex, and mutex stands for mutual exclusion. So you start a lock thread, you initiate a lock thread, and then right before you actually access the critical section, you will lock basically by saying lock and point to the mutex, and once you're done with the critical section, you unlock. So a lock is basically just a variable, and this is basically right now you're creating a lock of the type mutex or mutual exclusion. And now you lock again and unlock when you're done. And in this case, exactly only one thread will be able to change balance while you have that lock. So no matter what happens with the compiler, no matter what happens with the scheduler, the thread that acquired this lock first will always be the thread that changes balance first. Okay, so you can of course use it for other data structures and data types, and you basically in the TCP you have two linked lists. One of them for basically threads that are waiting for the lock, or two data structures in general. So you have basically a list of all threads that are waiting for a lock, and a list of the threads that actually have the lock.